multi-part problems in physics. These are problems where you have a decision to make. You have to make critical decisions and pass variables forward from one part of the problem to another. They can be in one dimension or two dimensions. They may differ from pursuit and collision or interception and intersection problems because those problems refer to multiple objects traveling at once. So there's a slight difference in these. The most common cases would be cars accelerating to cruise control and then maintaining constant speed. We can toss a ball upward and find that it's much easier to break into phases of journey, falling and then decelerating, jumping and landing again, falling and jumping before landing, landing on airbags, transport trucks hitting a runaway lane. There's all sorts of variations of this problem. So here's an example of one. Top fuel dragsters have some of the highest acceleration of cars known, and they will accelerate from rest to 338 miles per hour in under 3.7 seconds on a 305 meter track. I watched Brittany Force's race, and by my timing on the video, the car took 15 seconds to stop once the parachutes opened. So we need to break it into two phases. Under its power, during the acceleration phase, and then when the engine's cut and the parachute deployed. Let's take a look at the solution for the acceleration phase. We have been given a distance, a starting and final speed. We need to calculate the acceleration, and we know the time to when she completed the race. Using these calculations, I can work out that the acceleration of the vehicle was about 4.5 Gs. Now, what do we pass forward to the next equation? She's at 305 meters and she's traveling 151.17 meters a second at the moment she crossed the line and then deployed her parachutes more or less at that time period. So the VF from the first part moves forward and becomes the VI in the second part. And her new VF will be 0 when the vehicle stops. When we calculate it, we find that she will take 1,134 meters to stop again. The acceleration on these vehicles is rather brutal. You can see what happens to the tires. Now, these tires are intended to do that, but nonetheless, it's pretty impressive. Next year, you will be able to calculate the kind of acceleration as the tire spins around in a circle. And that's with this formula here, which will be the only new variation on acceleration that you do. I would encourage you to watch this video clip of what happens to the tires when the engine starts accelerating. Let's move to a slightly more advanced problem, jumping down. Here's an example of a man landing after a jump. He leaps from a 4-meter platform. The moment his toes touch the ground, he decelerates to a stop, squatting down 1.2 meters. That is his stopping or decelerating distance. We want to know the time of the event and his landing speed, and as well compute his deceleration. The problem breaks into two clean pieces. We cannot do this in one pass because during the leap he is subjected to gravity accelerating him downwards. On the second part, when he hits the ground, he is now subject to an upwards acceleration, slowing his speed down. So it cannot be done in a single pass. We look at the falling portion. He starts by being 4 meters up. Now he's going down, so he's actually falling down 4 meters. We're looking at what happened, not where he is. He starts from rest. We don't know the final speed. We know acceleration, and we have to compute time. What do we know that we can work with here? Well, a fairly obvious one is d equals 1/2 at squared. Where's the rest of the term, the VIT? Well, VI is 0, so the VI term is gone in this case. This will be enough for us to compute the time it took him to drop. We rearrange, put in our variables, solve. Notice the sign convention that he went down, the two negatives canceled, and we were not dealing with a negative square root. And we get 0.89 seconds to fall. Now, the next part is we were asked to find his final speed. If we examine these variables, we have enough information provided at the beginning to compute his final speed, which is nice, because if we can avoid using time, we avoid using a calculated value. And you run it through this equation, and you get his landing speed is 8.9 meters a second. That's relatively fast. Take it in your head, round it to 9, multiply by 4. That's 36 kilometers an hour. Not quite 36, but it's up there. So this is a pretty, rapid landing. It doesn't look so bad in the picture because it is not to scale. That is not 4 meters based on the average height of a male. Okay, it might be 4 meters to me, but not on the average guy. That's definitely too short of a jump. 4 meters is quite a distance to fall, so he hits the ground moving fairly quickly. What happens to this 8.9 meters a second? This becomes the initial speed in the second part of the problem. The second part is a brand new problem. A man hits the ground at 9 meters a second. He crouches for a stopping distance of 1.2 meters, and he winds up coming to a halt in that time. It's a totally new problem. Nature has no memory of how he reached 8.9 meters a second. So that's the trick. This is now the new VI, and acceleration is not due to gravity now. It's being provided by his legs. We get an acceleration of 67 meters per second squared up. That's 6 G's. That's a pretty tough landing. All right, this is basically, you have to going to parkour it and roll. If you just jump down and squat like that, that is really going to hurt. That's a pretty hefty acceleration for a human body. Now for time, we can also again avoid using a calculated value. My favorite is the D equals V average times time. And we get about 5.3 seconds. Now, does this seem reasonable to you? Does it seem reasonable that we have a time of 5.3 seconds to stop? Does that seem correct? What mistake have we made here? Take a look at my math. Take a look at my answer. What did I do wrong? There is no way on earth that stopping in a crouch and going from 9 meters a second to 0 in 1 meter distance took 5 seconds. That is just not possible. Do you see the mistake? There's only one way to get 5.34. We wound up multiplying, not dividing. And this is the kind of alarm bell I want to hear go off in your head. So we fix it. We go in and it's not right. 1.2 divided by 5.34 equals 0.22 seconds. Now that seems better. Now, 0.2 plus the 0.89, this would be 1, 1, 1. If we're tired, let's double check. Isn't that convenient? See how easy it would have been for me to slide that mistake right past you and you not notice? But you think about it. Hold on a moment. Didn't you say in the last problem it took us nearly a second to fall 4 meters, and now it's going to take us 5 for the last meter? That there was something wrong with the number. That's when you're doing physics, when you look at the number and go, it's not reasonable. So the total time was 1.11 seconds. And there's really good odds of broken ankles at 6G. If you didn't land bang on correctly, you just struck your keister on the ground real hard. That is not a nice acceleration to subject your legs to. What about, we're going to look at a scenario where they jump upwards at 5 meters per second. We'll have to break the problem down. They will reach a maximum altitude d when their speed falls to 0. At that point, they begin to fall towards the ground again, and we will pass forward the distance and the speed from the first part to the second part. They begin to fall from the height they achieved in part 1, and the VF of 0 in part 1 becomes the initial speed in part 2. This will continue on to part 3, where the final speed in part 2 becomes the starting speed in part 3. The distance now, though, has nothing to do with the jump. This man has landed on his feet, and the distance of 1.2 meters down is due to him crouching. So we'll start off first by calculating the time of flight to the peak. We rearrange the acceleration formula, and we get 1/2 of a second. This makes common sense because you leapt at 5 meters per second up, and gravity removes 10 every single second. So it's only going to take gravity 1/2 a second to stop you. We put it into the time-independent equation. That way we avoid using a calculated value, and we get that they will travel only 1.25 meters up in that 1/2 a second. So it's much less than his body length. He's only jumped up 1.25 meters, so he's barely cleared his own shoulders. Don't forget, though, if we want the absolute distance from the ground, we need to add the platform height on. So he is now positioned 5.25 meters up from the ground. That's his total altitude from the ground now. So in part 2, he falls all the way to the ground. We use the time-independent equation again, and we get that he's going to hit the ground slightly more than 10 meters per second because of this fairly large fall. We put that speed forward into part 3, and we can also calculate the time it takes him to fall all the way to the ground as 1.2 seconds. He leapt up for 1/2 meter a second, and he fell for 1.2. This again seems reasonable because his leap was only 1.2 meters, not what the diagram is showing you, him clearing his own body height by many times. On a 2-meter tall man, 1.2 meters, he barely got his feet up to where his knees were. So he fell much further than he jumped. So the falling time is quite a bit longer than the time traveling upwards. Landing, we now have a completely new problem. He hits the ground at 10 meters a second, and he stops himself in 1.2 meters. There's no time, so we use the time-independent equation. And we get 43 meters per second squared is his landing acceleration. That is 4 Gs. that's probably going to really damage his knees. That's getting up there. In fact, it's unlikely he stood. When he hit the ground, for your knees to buckle you at 4 Gs and stop you, he probably struck his butt on the ground, or his legs simply collapsed and he walloped into the ground. I doubt most people could actually carry out a smooth landing. You'd probably have to do one of those parkour tumbles to do it. Now, it would be trivial at this point to calculate the last time interval. It'll be short, but we weren't asked for it. Trampolina is a slight variation on this problem. She believes in saving the environment, so she took a 4-wheel vehicle to the top of a mountain in the rainforest to trampoline to save the whales. She succeeded in jumping 4 meters in the air and personally estimated that she saved the blue whales in the process. Anyway, given a jump 4 meters up, how long was she in flight? And if the trampoline stopped her in 0.5 meters, what deceleration were her legs subject to? I don't like word problems like that. I just made it to be a jerk. This kind of problem just really buries the physics. So your best bet when someone's gotten really wordy and is not providing you information in the problem is just highlight where the info is and strip it down. This is the same problem as the other guy. I'm just illustrating it in a slightly different way. There's no difference in these two problems, just a few numbers. But I've decided to break it down so maybe you see a little bit easier. If it doesn't work for you, that's fine. 2 different ways of showing the same kind of result, breaking a problem into steps. So she launches with a VI on the way up. She ends with VF equals 0, and we said she somehow managed to clear 4 meters in the gravitational field of the Earth. Then she begins to fall. So this VF of 0 becomes the VI of 0 in the next problem. The launch of VI will end with VF over here. By symmetry, whatever speed she jumped with, it went down to 0, and as she falls, she will regain all that speed. I colored them both green because those values will repeat by symmetry. The third part, there is no symmetry. She hits the pad at VF, which is what she jumped from, and now she comes to a halt. VF equals 0 in a drastically different distance. So these two parts are mirror images of each other. The third part is not. Exactly like the man jumping from the 4-meter block. So let's start this one step at a time. Without reference to time, we have no choice but to use this equation. We put in the VF of 0, and we can compute that in order for her to jump 4 meters straight up in the air, she would leap with 9 meters a second. Okay? Now let's think about this. You jump at 9 meters a second. Gravity is going to take away 10 of that in the very first second. So she will barely make 1 second up before she stops. The average speed between 0 and 9 is 4.5. So she will be traveling an average of 4.5 meters a second for 1 second. This speed would agree to put you at about 4.5 meters in altitude when I rounded gravity to 10. So 8.9 meters a second for a 4-meter jump seems very logical. The time will come from the acceleration problem, and we get 0.9 seconds. Okay? So it works out really well if you do your head estimation. What happens now is the reverse of the problem. She falls, and she will go back from 0 speed to 8.9 meters a second in 0.9 seconds. It will be an exact opposite track. However, can you claim symmetry and just do that? With me, yes. With other teachers, they may say, no, I need proof. So you got to check with each teacher you have. Now we're back where we started from. She's landing at minus 8.9. So we pass that value forward into this equation's VI. And once again, the time-independent equation will show up. There's about 3 equations you can use. The best way to do this is start with your time-independent one, because you really don't have much choice. Her deceleration value is huge. It's huge. It's a positive 80. That's 8 G's. She definitely slams her face. In fact, I would say this is probably close to puncturing the thing. That means that trampoline surface is having to force up on her as if she was 8 times heavier than before. So her feet have struck that thing at 8 G's. That would be like putting 7 more of her on her shoulders and standing on that trampoline. That's a lot of acceleration for the trampoline to make. How come it's positive? Because it's trying to reverse her. She's going down a negative in speed, and it's trying to turn her around to 0 or another velocity very quickly. So the acceleration is opposing her downward speed. And then we calculate V average t, and we get 0.11 seconds. This makes sense that she's having to stop in an extremely short length of time. Now, if we wanted to verify we are correct, we could take an equation we haven't used and shove in the values we had, this calculated value, and the acceleration we get is pretty much the same as in the step up here. So this is another way. It's the exact same problem as the man jumping upwards from the 4-meter pillar. It went through the exact same sequence of steps. Here's another example of an overly wordy problem. Ephigenia graduates from applied cosmetology and throws her cap in the air. Assuming her cap is a point particle and air resistance is negligible, and she throws the cap at the initial speed of 4 meters a second. How high does the cap fly and how long before it touches the ground? Ephigenia is 1.3 meters tall, 40%. Useless information to us. We must itemize. Going up, there's a starting distance of 1.4 meters. How high does the cap fly? We have to calculate. We know it's at 4 meters a second, and it drops to 0 under the influence of gravity. What height did she throw the hat on? Well, we can sort of assume she threw it from head level. Right? I drew that line on there. This is where sometimes these wordy problems, it doesn't make it clear. If the problem is over wordy and over creative, it doesn't make it clear where it started from. So we're starting from 1.4 meters, and she throws her hat up at 4 meters a second. We can break it down rather quickly. We've been given enough information here to compute time right off the bat. And that's always nice if you can do time right away, because it opens up all the equations. When you don't have time, you're stuck only with that VF squared equation. So if you see a chance to snag time first, that can give you a lot more options later. And then we can use D equals V average T, because I feel being risky. We're using a calculated value. It's like, ooh, don't you feel the thrill? And so V average T, we get 0.8 meters up. But, don't forget, that's up from where she threw it. So that does put her a little bit higher. It makes her a total of 2.2 meters up in the air from the floor. Then there's going to be the symmetry of the cap returning to its original level. We did that on the previous problem with the trampolina. We did not do it on the problem with the guy jumping off the building. There are many ways of doing it. Do you feel risky? Why don't we try it all the way down, all at once? Yes, shall we? Why not? So, from falling from the peak to the floor, what do we have now? Well, the 2.2 meters that the hat is up now needs to undo itself. It will fall 2.2 meters. That's why it's negative. It starts at rest when it's up here. The VF there becomes the VI here, and we have two calculations to make. Once again, this guy is the easiest one to do. Why didn't I solve for time first? I can't in this case. I didn't have the final speed, so I'm stuck on trying to find time. So I do have to solve for final speed first. Her hat hits the floor at 6.6 meters per second. And now we can calculate the time of 0.7 seconds for the fall. That gives us 1.1 seconds for the entire journey. So that's one way of doing it, where you do it in just 2 passes, not 3. A final word is this 6.6 meters a second came out positive. And that doesn't make a lot of sense because it's on the way down. And so it should be negative. Now what happened? If we look here, I was very careful at putting the correct signs on, and mercifully we wound up with a square root that had a positive under it. So our calculators will execute that square root. No problem, except you do realize now you're going to get positive values no matter what. So what are we going to do with that positive 6.6? You have to manually decide it's down. If you recall your math teachers, a square root of 100, the answer is not 10. It's positive 10 and negative 10. Every square root has a positive and a negative root. And in math class, you write them both down. In physics class, one of them is generally an illusion. Not always, but in this case, positive 6.6 meters per second makes no sense. And you have to manually make it negative. Romeo goes to Juliet's window and throws a stone at 20 meters a second towards her balcony, which is 16.2 meters above him, and he is 1.2 meters in height above the ground. The graph is a distance time graph, not a height versus distance graph in this case. He is throwing the rock almost vertically. At what time and speed will it land on her balcony? How high did the rock actually fly? You can tackle this problem in 2 ways, a single problem with one equation, or break it into 2 problems. The first would be from Romeo to the peak altitude, and the second part would be a straight drop from that higher altitude to Juliet's balcony. If we wanted to set up the equation of motion, we would be setting up d equals VIT plus half AT squared, but we're tossing in this starting height, which we can call d naught or d original. If I plot this with the values put in there, Romeo's height, the speed he threw the rock, and the acceleration due to gravity, and I plot it on a program like Desmos, we see there are 2 solutions for it where the rock reached the correct height. This makes logical sense because the rock passed her balcony on its way up and on its way down. So we typically get double solutions, but only one of them is the correct one for physics. The downward speed, because it has to land on her balcony, not pass it on its way up to heaven. The first part of the problem is to peak altitude, which means VF is 0. The speed will go from 20 to 0 at a rate of negative 10 every second. So it looks like 2 seconds of flight should be it. And we set up the acceleration problem, turn it to time, and there it is, 2 seconds. If we want to take a risk, we can use that calculated value and find the stone makes it 20 meters up. Or we can use d equals VIT plus half AT squared if you want to torment yourself, and you will get 20 meters up. The important part, though, is don't forget to add Romeo's height, and we get 21.2 meters in altitude, is when the stone stops. Now the stone falls to the balcony. And falling to the balcony, it has to fall from 21.2 meters to the 16 meters in altitude, which is a minus 5.2 meters starting from 0. This would give us a final speed of 10 meters per second down. Once again, the square root would have told us it was positive 10 meters per second. You have to choose the negative root to make it make sense. Taking d equals v average t, I can rearrange, solve for the time, which is half a second, and we add it to the original 2 seconds up, and we get 2.5 seconds. If we try it in one pass, we would have to set up the equation saying the distance is equal to the starting distance plus the speed and the acceleration's effect on it. And we would get a quadratic that we could quickly reduce and get an answer of 1 second or 3 seconds. And it will deliver both answers to us using the quadratic formula. Let's look at some simulated data from a rocket. It's very important to recognize that this is now a distance time graph again. We have to be very careful as we move into advanced physics that sometimes these are trajectory graphs, meaning distance on the vertical, distance on the horizontal. We have a rocket that lights its engine and accelerates for 10 seconds at 40 meters per second squared, at which point the engine shuts off and it coasts to a maximum height and then begins falling back to Earth. This plot is showing height against time. Make clear of that. We're going to have to compute the distance, the speed, and the time at the points indicated. The key is to recognize that this problem breaks into 2 distinct phases. The first phase is in that first 10 seconds when you see the little blue dots are together when the rocket is accelerating. And the second phase occurs when the engine's cut off and the rocket coasts and is now only subject to gravity. So we have 2 phases, the boost phase and the coast phase. In NASA terminology, they call MECO, or main engine cutoff, when the rocket is finally on its way to space. Let's begin to analyze what information we have. During the boost phase, we don't know the distance yet. We know the rocket starts off at 0. We'll have to compute the final speed given the acceleration of 40 meters per second squared for 10 seconds. And that's easy. If I pay you $40 an hour for 10 hours, that's $400. The answer is going to be 400 meters per second. But you have to prove it to your teachers. So we stick it in the acceleration formula, rearrange, and we get 400. Now we move down into the d equals 1/2 at squared. We knew the acceleration to begin with, and we knew the time, so without any calculated values, we can find the time as 2,000 meters. Let's use our common sense again. The rocket peaked at 400 meters a second from 0. So its average speed in the boost phase was 200 meters a second for 10 seconds. That's 2,000 meters in height. It's perfect. So that's what happened in the first 10 seconds. Now these values will have to get passed forward into that coast phase. So which values get passed forward? The final speed during the boost phase now becomes the starting speed in the coast phase. And the problem starts at an initial altitude of 2,000 meters now. Gravity is providing the acceleration. Then we're going to go for the maximum height. And the maximum height will occur when the VF falls to 0. So here's our setup for that part. We can solve for time, and we get 40 seconds. That makes good sense. You're losing speed at 10 per second starting from 400. 40 seconds to the peak altitude. And the average speed times time gives us 8,000 meters higher than when we started. So this now means it's 10 kilometers in the air. We are only halfway up though. The reason I colored the whole coast phase is I didn't like the look of it being half colored. This is only halfway up. We got to go ahead and do the other side of the problem now. So starting at 10,000 meters with a speed of 0, what is our impact speed and time to fall going to be? We will reach 447 meters a second down. How come it isn't the same speed we started with? Because we were starting from the end of the acceleration phase. So this problem started here to the peak, and the second half goes from the peak not to the same height, but all the way to 0. So it's not a symmetrical scenario. It's landing slightly faster than when it started this part of the journey. That's sensible. And we get 45 seconds. It makes good sense. And then you could add them all up and get your total if you required. Here's a new problem, overtaking. An overtaking problem like this one is exactly the same as the pursuit and collision problems in the first part of kinematics. The only twist is that the car has two different behaviors, an acceleration phase and a cruise control phase, and this forces us to break it into two parts, and there is no way around that. Let's itemize what we've been given. We know the speed starts at 5.5 meters a second and it continues to a peak speed of 33.3, which will persist throughout the problem. Given that this car's final speed is slightly higher than the truck's constant speed, the car will definitely intercept at some point. If this speed here was, say, 29 and that was 30, then eventually the car cannot possibly catch up. Given the acceleration of 3.15 meters per second, it's pretty trivial to figure out the car is accelerating for 9 seconds. So what if we try to solve this in one pass and use the quadratic and solve for distance this way? This is a very common mistake. The person decides, I'm going to set it up exactly like the pursuit problems before. These two vehicles will have identical positions when they meet each other or collide or successfully intercept. The truck will be at location, speed of the truck times time plus the 600 meters head start the truck has. The car has an initial speed times time plus 1/2 AT squared, and this should allow us to solve it. It'll need the quadratic, but this would be like the number one mistake I would see, and you're probably looking, where is the mistake? The mistake is the idea. The big mistake here, you will not find it no matter how much you manipulate the math. The mistake was not understanding the problem. This assumes that the car will always be accelerating during this problem. you will get a time value that will solve, but only if the acceleration continued throughout the problem, and it doesn't. The car is only accelerating for 9 seconds, so it's the idea of using a one-step solution that's the problem. And once you do that, you will not be correct from that moment on, and you can have your math double-checked and it will be perfect, but you've answered the wrong question. We can't use this equation because it's a constant speed problem. So we are forced to break it in two. And if you don't see that, you waste your time. One of these two will work. Proving it to you, if we use this one, we get 175 meters. If we use the other formula, we get 177. Why did they depart? Because I rounded the time. Either one of these equations worked. During the acceleration phase, the car has traveled about 175 meters. The same 9 seconds, though, the truck has had an opportunity to continue driving. So while the car was accelerating, the truck actually covered 270 meters of ground. So the car is literally further away than when it started because it was traveling much slower than the truck and had just barely exceeded the truck speed in 9 seconds. So it makes sense that the car has lost ground, but it won't stay that way. Once the car is at constant speed and it's only 693 meters behind and it's traveling 3 meters a second faster than the truck, it's going to win. And you can think about this one. The car is doing 33 roughly. The truck is 30. 3 meters a second, and there's 693 meters between them. I think you could estimate in your head how long before this problem ends. But we need to see it by math. The truck is 693 meters in front of the car. That's the back end of the truck to the front end of the car. So if we want to do this properly, we have to add the 50 meter length of the car plus the 5 meter length of the car onto that, and we get 748 meters plus 10 more meters, it said, for a safety margin. And this is where a problem becomes bean counting. We said we had to pass with 10 meters spare, so we have to add a few more things along the way. But this isn't hard, you just have to remember to do it. Now we can solve for two equations. At this point, we have the calculations from the previous page for the first 9 seconds, and now it's just a generic pursuit problem. The car's on cruise control, V of car times T, and the transport truck, it's speed of the truck, VT, plus the truck's lead. And this is not the condition of collision. This is the condition of a clear 10-meter pass, including the length of the vehicle bodies. Let's start rearranging. This and that are just labels. They can be dropped. This is the equation. We gather terms. We put in the speeds. We get a solution, 230 seconds. At 230 seconds, the car will have passed the truck. Now, what happens if you goofed and you decided to put the head start of the truck and mistakenly you put the head start of the truck on the car? You didn't write the speed of the car times time. You did the speed of the car plus its lead. And if you did it backwards, you would get a negative time. Same value, but negative. And that would be the warning sign you messed up. The mental shortcut you could take is to do differential velocity, a fancy way of saying what's the difference between the two. The car's at 33, the truck's at 30, so their differential speed is 3.3 meters a second. The car is traveling at 3.3 meters a second with respect to the truck. Okay? Under that case, you could solve it in your head. And you could get the same thing as 229 seconds to pass. Now, how far did everybody travel in this time? Well, the car was traveling 33.3 meters a second for a whole 229 seconds. The car has driven almost 8 kilometers on the road to pass the truck. And don't forget to toss in the numbers from the first 9 seconds. I want to take a moment and look at the distance time graph of the car. In the first 9 seconds, you can clearly see the car is accelerating. The plot is quite obviously a curve. But if we put the truck on this graph, something will happen that makes it look confusing. When the truck and the car are both put on the same graph, the presence of the truck makes Desmos compress the vertical to show all that distance, and the car's curve in that first 9 seconds is starting to look like a straight line. And you might go, but there's no acceleration. Yeah, there is, but it's being squeezed off the graph. And it gets worse if we back out. If I back out to 250 seconds, you can see there's a little tiny visible patch of acceleration down here that you can only see the thing is curved because you know it's there. You see what I mean? Tiny little bit of curve. Apart from that, it's cruise control the whole way. The line straightens out. And sure enough, they cross at looks to be about 240 seconds. Reading graphs is as much of a skill as reading words. We are going to try 3 scenarios now. Dropping the ball, throwing the ball down, and throwing the ball up at the same speed, and see the difference in the results. First of all, let's get a ballpark figure. We're falling 100 meters. Gravity, approximately 10. If you fall for 3 seconds, your speed will be 30. Gives you an average speed of 15. 45 meters. If you fall for 6 seconds, you'll reach 60. Average speed is 30. So about 180 meters. So it looks like it's around 5 seconds to fall that far. It's not that hard to do. Itemizer variables. It's falling 100 meters, so it's a negative, and acceleration is in the same direction. Start some rest. Now we're going to get a formulated here. We can use this one right out of the gate because it's going to reduce beautifully to 1/2 AT squared. You could write 1/2 GT squared, and that's totally acceptable. It's gravity. And that tends to make it harder for you to mistake some other value for the one you're using. And you solve for t, put her all together, 4.5 seconds, and we guessed around 5. So see, not so hard. Take that time, put it into the equation, and we get 45 meters a second down. That's going to hurt, right, if it hit you? Highway speeds, think 28 to 30. So this would really be injurious if you got hit by it. Let's look at the throwdown. When we're going to throw it down, we're going to add speed to it. Everything's going to be in the negative now. Can we guess the time like we did last time? Yes, with a little bit of thinking. We are adding 5 meters a second to a speed that we guessed to be 50 meters per second on the last problem. So what's 5 compared to 50? It's about 10%. So it's running about 10% faster. So we guessed about 5 seconds last time, so taking off 10% of that is 4.5. If we go to 4.47, the exact amount, and we subtract 10%, it pretty much brings us to 4 seconds. But we're going to formulate this. Why not use the quadratic, eh? Find out it's kind of difficult not to use it here. We set her up. You're allowed to drop the units there. And, hey, reduce it. Why carry big numbers if you don't have to? At this point, you might not like looking at it because you're used to seeing x's. Be my guest. Put in the x's. And we bring the quadratic formula out to play, and it says 4 seconds. It also gave a negative time, but we don't care about that one. We only want the positive time. The negative time wouldn't mean anything. And then, knowing the time is 4 seconds to fall, which is pretty much our guess, we can take the initial speed, add what's acceleration going on to it, and we get 45 meters per second. Wait, that's like barely faster than last time. Well, yeah, you probably thought it was going to add straight up and come out to about 50, didn't you? But think about it. The 5 meters a second extra speed took away some of the acceleration time. And so, because you threw it faster, gravity couldn't grab it as long, and it kind of doesn't work out the way you would think intuitively. That's normal. Now we're going to throw up. I'm sure you feel like it at this point. We're going to toss the ball straight up at 5 meters a second and see what happens now. Can we do the reverse now and go, you know, the first time we guessed that it was about 45 meters a second, so would this make it 40? I don't know. You have to think about this one. Is this problem really different from the last one? It's not nearly as different as you might think. So we'll do the formula, get in our values. The only thing that seems to have changed is this term here is now positive. Reduce, switch it to x's if you're more comfortable, pop her in the quadratic, and we only get 1 second longer. And we wind up with an impact speed the same. It's literally going to hit the ground at the same speed the previous one did, but with a 1 second delay. That's not a coincidence. And that's our what the physics moment for the day. Look at the symmetry again. He got the same landing speed. All that changed was the time. Symmetry, my friends. There's the symmetry in the problem. The ball went from 5 to a peak of 0, and it fell back to 5. And so it winds up being the same as if he just threw it down at 5 meters a second. The only change was a time delay. It takes half a second to go up, half a second to come down, so there's only a time delay that took place when you threw it upwards. The symmetry here means up, down symmetry, and then there is the fall. And that's why you got the same landing velocity as the throwdown. The throwdown was this phase here. So the throwdown condition has been tacked on to this one. And that's why the landing speeds was the same. This thing went from 5 meters a second all the way down as if it had been thrown down from the beginning. Now, could you try this one in one pass? Just do one big giant pass. Yeah, but it's going to need the quadratic formula if you decide to do it in one pass. And you'll miss a lot doing it that way. Now, I didn't include the height of the person. I didn't let you include the height of the child, where a lot of people would put it in there. But does it matter? Well, once again, look at the scale diagram. Those pictures I showed were not to scale. This one is. And I've made this person 2 meters tall. I put a box there to make it easier to see. On the scale, written on the diagram, this is true to scale. So do you really think skipping their height would make the problem much difference? This is 1/50th of the height. That is literally a 2% change. Rounding gravity from 9.8 to 10 is also a 2% change. To give you an idea of how much it affected things, this is the solution if we ignore the person's height. This is the solution if we include their height. That's the difference. That is pretty much well below human reaction time. You have to make a change of 1/10 of a second before a person could even possibly contemplate noticing it or reacting to it. This is an extremely small time difference. So yeah, the person's height is pretty much irrelevant given the height of fall here. On the throw down and throw up problem, all that happens in the quadratic is this thing changes a bit. And you get, 4 seconds goes to 4.01. 1/100th of a second. 10 times smaller than your reaction time. So in other words, the problem changed 10 times less than what you could do with your stopwatch. And that's why we're quite safe ignoring the person's height on a 100-meter tall building. Why is the change so little? Because of these square roots. You changed initial numbers. This 102 was 100 before. That's a 2% change. But after it goes through the square root, the change was only from 4 to 4.01, 0.25%. And on the other times, for the throw up one, it was 0.89%. Why did the change disappear? Because the square root squishes change. So this is where detailed calculations are wasting your time, because you can demonstrate it's not affecting the problem much. Now, this would not be true if the boy threw the basketball down from a 20-meter height. Then his height would be relevant.